please will you join me in giving a very warm welcome to our speaker this evening, Professor Robin Wilson, as I invite him to deliver this evening's lecture.
Thank you very much. It was in 2006, when I was Gresham Professor of Geometry, that I conceived the idea of an annual joint lecture with the London Mathematical Society. Since then, an impressive list of speakers have lectured on a wide range of topics, and I feel very privileged to be giving the latest of these joint lectures today. Equations are the lifeblood of mathematics, and I've recently enjoyed exploring how some of them arose. Their stories often tell us much about the cultures from which they emerged and the individuals who struggled to discover them. In this lecture, I've chosen 5 of my favorite equations to share with you. Some will already be familiar to you, while others may be less so, and they arise from different areas of mathematics. The first equation takes us back to our school days and straddles the areas of geometry and algebra. This theorem for right-angled triangles is one of the best known and remarkable results in mathematics with a wide range of applications. But where did it come from, and what has it to do with Pythagoras? As shown here, it tells us that for a right-angled triangle, the area z of the square on the longest side is the sum of the areas x and y of the squares on the other 2 sides. So it's the result from geometry. But if the triangle has sides of lengths a, b, and c for the longest side, then these areas are a squared, b squared, and c squared, and we can write the theorem in algebraic form as a squared plus b squared equals c squared. But such an equation would have made no sense to Pythagoras or his contemporaries. An example is the right-angled triangle with sides 1, 1, and root 2, where 1 squared plus 1 squared is root 2 squared, while 2 other well-known examples have sides 3, 4, 5, with 3 squared plus 4 squared equals 5 squared, and 5, 12, 13, with 5 squared plus 12 squared equals 13 squared. Pythagoras was born around 570 BC on the Greek island of Samos, and he moved with his followers to Crotona, now in Italy. The Pythagoreans explored mathematical proof, but no surviving evidence lists specific results to them or to Pythagoras himself. And so many historians prefer to call it the Pythagorean theorem rather than Pythagoras' theorem. But although the Pythagoreans may have been the first to prove the theorem, the result had already been known in Mesopotamia a millennium earlier. The Mesopotamians, or Babylonians, wrote with a stylus on clay tablets, and many hundreds of mathematical tablets have survived. Their number system was based not on 10, but on 60, which survives in our measurement of time, with 60 seconds in a minute and 60 minutes in an hour. This clay tablet, from around 1700 BC, shows a square with its diagonals and the base 60 numbers 30, the side of the square, and 42, 25, 35, the length of the diagonal. From this, their value for root 2 was 1, 24, 51, 10, which in our decimal system is correct to a remarkable 5 decimal places. The ancient Chinese were also familiar with the result, as illustrated by their broken bamboo problem shown here. A bamboo, 10 chi high, is broken, and the upper end reaches the ground 3 chi from the stem. Find the height of the break. To solve this with our algebraic notation, we let h be the height of the break. Then one side of the triangle is 3, and the longest side is 10 minus h. Then, by the Pythagorean rule, h squared plus 3 squared is 10 minus h all squared. And solving this equation gives the answer of 4 and 11/20 chi. There are hundreds of proofs of the Pythagorean theorem, and we'll look at 3 of these. Several civilizations have used dissection arguments to obtain the result. So here are 2 dissections of a square with side a plus b. Each dissection includes 4 right-angled triangles with sides a, b, c. And removing these triangles leaves squares with areas a squared and b squared on the left, and a square with area c squared on the right. So equating these areas then gives a squared plus b squared equals c squared. Our next proof is due to James Garfield, later the 20th US president. It apparently came to him during a mathematical discussion with members of Congress. Garfield took 2 copies of a right-angled triangle with sides A, B, and C, placed them end to end, and joined their top corners, forming a trapezium with vertical sides of length B and A, and base A plus B. The angle between the sides of length C is then easily seen to be a right angle. Now, the area of this trapezium is the product of its base and its average height, which is A plus B times a half A plus B. While the total area of the 3 triangles is a half AB plus a half C squared plus a half AB. And if you equate these areas and simplify, that gives a squared plus b squared equals c squared. In Euclid's Elements from the 3rd century BC, Book 1 builds up to the Pythagorean theorem, and its proof is an impressive display of the style of geometrical argument that permeate that seminal work. The main ideas are as follows. In the diagram on the left, the vertical line from A down to L splits the lower square into 2 rectangles. Using congruent triangles, as indicated on the right, Euclid proved that in the lower square, the left-hand right angle has the same area as the upper left-hand square. And the right-hand rectangle has the same area as the upper right-hand square. It follows that the sum of the areas of the 2 upper squares is equal to the sum of the areas of the 2 rectangles, in other words, the square. They form the lower square, and this is the Pythagorean theorem. How can we generalize the Pythagorean theorem concerning right angles in the plane? Can we extend it to 3 dimensions? Here's a rectangular box with sides A, B, C, and with a diagonal of length D. Applying the Pythagorean theorem to the right-angled triangle ACD gives E squared is A squared plus B squared. And applying the Pythagorean theorem to the triangle ACE gives D squared equals E squared plus C squared. Eliminating E squared then gives A squared plus B squared plus C squared equals D squared, which is a 3-dimensional Pythagorean theorem. So for a cube with side 1, we have 1 squared plus 1 squared plus 1 squared is root 3 squared. And an example with integer lengths is 3 squared plus 4 squared plus 12 squared equals 13 squared. Here's a problem posed by the British puzzler Henry Dewdney in 1917. It concerns a spider and a fly. A spider is at a point A of a rectangular room on the right, with dimensions 30 times 12 times 12 feet. And a fly is at B on the left. What is the shortest distance that the spider must crawl to catch the fly? Well, one route is for the spider to descend to the floor, 11 feet, cross it, 30 feet, and climb up to the fly, 1 foot, giving 42 feet in total. But can we do any better? Yes, we can. By flattening the room, with the spider taking the direct route shown. This involves total horizontal and vertical distances, horizontal 32 feet, vertical 24 feet, then giving, by the Pythagorean theorem, a distance of d is the square root of 32 squared plus 24 squared. And that works out at 40 feet, which is the correct answer. Can we also extend the Pythagorean theorem to higher powers? For example, can a cube be the sum of 2 other cubes, or a 4th power be the sum of 2 other 4th powers? Such questions intrigued the 17th century French lawyer and mathematician Pierre de Fermat, shown here, who used a clever argument to prove that there is no such result for 4th powers. Although Fermat further claimed to have proved that for any n greater than 2, the equation a to the n plus b to the n equals c to the n has no non-trivial whole number solutions, few people believed his claim. And despite many attempts at a valid proof, no one else could do so either. And indeed, it wasn't until the 1990s that Andrew Wiles, a British mathematician working at Princeton University, announced to great excitement that he had proved Fermat's result in all cases. Although a gap was found in his argument, it was patched up, and a 1,000-page proof was published in 1995. After more than 3 centuries, Fermat's so-called last theorem had at last been proved. Second equation. One of the most fascinating numbers in mathematics is the golden ratio, often denoted by the Greek letter phi. Although some of its geometrical properties can be traced back to ancient Greece, its description as golden did not emerge until the 19th century. In 1509, the Italian Luca Pacioli had ascribed religious significance to it, calling it the divine proportion. And a century later, the mathematician and astronomer Johannes Kepler concurred, describing it as a precious jewel and claiming it to be elemental to God's creation of the universe. What is this number? This number phi is the positive solution of the quadratic equation x squared equals x plus 1. And it equals a half of 1 plus root 5, or 1.618, etc. An irrational number that goes on forever. Now, because phi squared is 5 plus 1, we obtain its square by adding 1. So phi squared is 2.618, etc. And if we rearrange the quadratic equation as 1 over phi equals phi minus 1, we get its reciprocal 1 over phi by subtracting 1. So 1 over phi is 0.618, ... We notice also, I'll need this later, that 1 over phi minus 1 equals phi. That is 1 over 0.618 equals 1.618. Much of the interest in the golden ratio arises from geometry, but assertions about its geometrical origins are often ill-founded. For example, claims have been made that the proportions of the Parthenon in Athens and other Greek buildings were based on the golden ratio. Aesthetically, some buildings may seem too short and fat, or too long and thin, whereas a rectangular building with these proportions may be considered to have the perfect shape. But although the Greeks knew about the golden ratio, there's absolutely no evidence that they designed their buildings to accord with it. What is this shape? Well, a golden rectangle has side lengths in the ratio of phi to 1. And if from such a rectangle we remove a square of side 1, we obtain a smaller rectangle, the vertical one, with sides in the same ratio. This is because phi over 1 equals 1 over phi minus 1. If we now remove a square from this second rectangle and continue in this way, we can draw a succession of circular arcs that approximate a spiral pattern, known as the golden spiral. And this spiral converges to the point where diagonals of the first two rectangles cross. Such a spiral is a logarithmic spiral, which arises in nature in the form of nautilus shells, sunflowers, and elsewhere. The golden ratio also arises in other situations. For example, in a regular pentagon, the length of any diagonal is phi times that of a side. A triangle formed by two sides of the pentagon and a diagonal then has angles of 108 degrees and 36 degrees, and one formed by two diagonals and one side has angles of 72 degrees and 36 degrees. Moreover, phi can be shown to be 2 times cos 36 degrees. By combining these triangles in 2 different ways, the Nobel Prize winner Roger Penrose constructed these kite and dart shapes that you can see in the middle, that he used in the so-called Penrose tiling. And unlike the 3 regular tilings of the plane shown below, constructed from squares, triangles, and hexagons, Penrose's tiling never repeats however far we go. And it's also related, incidentally, to quasi-crystals in physics. Closely related to the golden ratio is the Fibonacci sequence, in which each successive term is the sum of the 2 previous ones. So you can see 13 is 5 plus 8, 21 is 8 plus 13, and so on. Born around the year 1170, Leonardo of Pisa has been known as Fibonacci since the 19th century. While traveling in North Africa, he learnt about the Hindu-Arabic numerals, which he then propagated in Western Europe in his influential Liber Abaci, or Book of Calculation. And as you can see from this page, the Fibonacci numbers appear vertically on the right. This book contained many mathematical problems, including his famous one about rabbits. A farmer has a pair of baby rabbits. Rabbits take 2 months to achieve maturity and then give birth to another pair each month. How many pairs of rabbits are there after a year? What you might call a hair-raising problem. As you can see, the numbers of pairs after successive months are the Fibonacci numbers. In fact, it's as easy as 1, 1, 2, 3. Interestingly, Fibonacci seems to have had no particular interest in this problem, and it did not achieve its popularity until the 19th century. But what has all this to do with the golden ratio? In the early 17th century, Kepler considered the ratios of successive Fibonacci numbers. These ratios, 1 over 1, 2 over 1, 3 over 2, etc., appear here in 2 columns. And as he discovered, those in the left-hand column increase towards the golden ratio, while those on the right decrease towards it, and their common limit is indeed phi. Here we see how the Fibonacci numbers can be arranged in a spiral pattern that resembles our earlier golden spiral, and further rectangles can be added at will. Also, like the golden ratio, Fibonacci numbers appear throughout nature. For example, the number of seeds in the spiral patterns you can see on a sunflower head are often Fibonacci numbers, such as 34, 55, or 89. An amusing paradox from the 19th century, or possibly earlier, was popularized by Lewis Carroll, mathematician and author of Alice in Wonderland. Here, an 8 by 8 grid of 64 squares is cut into 4 pieces, which are then rearranged to give a 5 by 13 grid of 65 squares. So where does the extra square come from? Well, the paradox arises because when we form the 5 by 13 rectangle from the 4 pieces of the 8 by 8 square, there's a small parallelogram in the center, whose area is that of one small square. And we can similarly cut and reassemble a 13 by 13 grid of 169 squares to give an 8 by 21 grid of 168 squares, but in this case, a square is destroyed rather than created. As you may have spotted, these numbers, 5, 8, 13, and 21, are all Fibonacci numbers. And for all similar examples, a single square is always either added or destroyed. And here you can see Lewis Carroll's own drawings of the general case, with various values for A and X, as you can see. To conclude this topic, I'd like to show you an unexpected feature of the Fibonacci number 89. The decimal form of its reciprocal, 1 over 89, begins with 0.011235, clearly exhibiting the early Fibonacci numbers. And indeed, 1 over 89 is exactly equal to the infinite sum shown in the middle, where you can see all of the Fibonacci numbers beginning to appear. Or in the form below, where the F's are the successive Fibonacci numbers. So this is a remarkable result, I think. My third equation is Euler's formula for polyhedra. A polyhedron, meaning many faces, is a three-dimensional object with polygons as its faces. So familiar examples are a cube with its 6 square faces, an Egyptian pyramid with a square base and 4 triangular faces. Such polyhedra have corners or vertices and edges, a concept incidentally introduced by the 18th century mathematician Leonhard Euler, who also presented this equation, as we'll see. There are just 5 regular polyhedra, where the faces are regular polygons of the same type, with the same pattern of faces at each vertex. 3 of these have triangular faces: the tetrahedron, meaning 4 faces, the octahedron, 8 faces, and the icosahedron, 20 faces. And there are also the cube or hexahedron with 6 square faces, and the dodecahedron with 12 pentagonal faces. These polyhedra are often called Platonic solids, after Plato, who described them in his dialogue Timaeus, linking them with the 4 ancient Greek elements of fire, earth, air, and water, and also with the universe for the dodecahedron. In 1596, another link between the heavens and the Platonic solids was proposed by Kepler. In his time, only 6 planets were known, and he suggested how their orbits might fit snugly around the 5 Platonic solids, as shown here. But his model was not widely accepted, especially when other planets were discovered, although his idea of a model for the universe did prove to be significant. Polyhedra also arise in nature as crystals of various chemicals, such as the cubic, octahedral, and dodecahedral crystals of iron pyrites. They appear to us radiolaria, which are the skeletons of certain marine sea mammals, and this attractive one has an icosahedral form. Returning to the Greeks, we find the 13 semi-regular polyhedra, where the faces are still regular polygons, but they're not all of the same type. For example, the truncated icosahedron in the center is made of pentagons and hexagons. These solids are often named after Archimedes, who supposedly described them in a work that's now lost. But in fact, these polyhedra were also investigated by Johannes Kepler, and here are his drawings. And he also gave them delightful names. For example, the large one, number 7, he called the great rhombicuboctahedron. Well, polyhedra come in all shapes and sizes. Here's a collection I found of some of what to me are the more attractive and interesting ones. But we now come to our equation, Euler's polyhedron formula, that if a polyhedron has V vertices, E edges, and F faces, then V minus E plus F equals 2, or in the version that Euler wrote, F plus V equals E plus 2. So, for example, a cube has 6 faces, 8 vertices, and 12 edges, and 8 minus 12 plus 6 equals 2. And similarly for a dodecahedron. And the result also holds for the semi-regular polyhedra. For example, as you can see immediately, The great rhombicuboctahedron has 62 faces, 120 vertices, and 180 edges. And again, the formula holds. How did it arise? Here's its first appearance in a 1750 letter from Euler to Christian Goldbach of Goldbach's conjecture fame. Goldbach's conjecture is a conjecture in number theory that every even number is the sum of two primes. So, for example, 8 is 3 plus 5, and 10 is 3 plus 7, and so on. And it's been proved up to, I don't know, 400 trillion or something like that. But there may be counterexamples, who knows. Anyway, paragraph 6 presents the result as h plus s equals a plus 2, where h is the number of faces, hedrai, s is the number of solid angles, or vertices, and a is the number of edges, achies, a term that he himself introduced. Surprisingly, the Greeks and Kepler never talked about edges in their writings, as far as we can see. And below, Euler applied the result to a prism, but failed to present a correct general proof. Euler's formula is sometimes attributed to René Descartes, who actually obtained a result from which it can be deduced, but who never actually did so. So I personally give the credit to Euler. Let's look next at polyhedra whose faces are all pentagons and hexagons. An example is the truncated icosahedron on the left, sometimes called a soccer ball, where v equals 60, e equals 90, f equals 32, and 60 minus 90 plus 32 equals 2. Such polyhedra interested the American architect Buckminster Fuller when designing his massive geodesic domes. And they also appear in a chemical context as fullerenes or Buckyballs, molecules that are named after him, Buckminster Fuller. Well, such polyhedra may have many hexagons, but if exactly 3 edges meet at every vertex, as in a soccer ball or a buckyball, then however many hexagons there can be only 12 pentagons. So let me prove that. Incidentally, they say that every lecture should contain at least one joke, at least one proof, and you should be able to tell the difference between them. So here, if there are p pentagons and h hexagons, then f, the number of faces, is p plus h. Then on counting up the edges around all the faces, we get 5p for the pentagons plus 6h for the hexagons. And that's equal to 2 times the number of edges, with the 2 arising because each edge borders 2 faces and is therefore counted twice. And on counting the 3 edges at each vertex, we similarly get 3v equals 2e because each edge meets 2 vertices. And that again is 5p plus 6h. If we now substitute these values into Euler's formula f plus v equals e plus 2, we find that the h's cancel and we're left with p equals 12. Something you might bear in mind the next time you see a geodesic dome or watch a game of soccer. Up to now, we've looked exclusively at polyhedra that can be drawn on a sphere, such as our soccer ball. But how about polyhedra drawn on other surfaces, such as a torus? That's the surface of a ring donut or a bagel. In 1813, a Swiss mathematician named Louillier was studying polyhedra with a tunnel bored through them. That is, polyhedra drawn on a torus, and proved that v minus e plus f is now not 2, but 0. For example, the polyhedron on the left has 16 vertices, 32 edges, and 16 faces, and 16 minus 32 plus 16 equals 0. And in fact, whenever we create another tunnel, the value of v minus e plus f decreases by 2. Another way of saying this is that for a surface with g holes in it, or equivalently a sphere with g handles attached to it, then Euler's formula becomes V minus E plus F equals 2 minus 2G. So for polyhedra on these two-hole surfaces shown, it's minus 2. And appropriately, the number 2 minus 2G that appears here is now called the Euler characteristic of the surface. My fourth equation is about counting combinations of elements within a set. Such issues form part of combinatorial analysis, or combinatorics, the branch of mathematics concerned with selecting, arranging, listing, and counting objects of various kinds. And here we meet some of these. Around the 6th century BC, a Sanskrit medical treatise noted that medicines can be sweet, sour, salty, pungent, bitter, or astringent. And its author, Susruta, explicitly listed all the possible combinations of these when taken two at a time. There are 15 such combinations, such as sweet and sour, sour and bitter, salty and pungent, and so on. He also listed the 20 combinations when taken 3 at a time, the 15 combinations taken 4 at a time, and the 6 when taken 1 or 5 at a time. And in general, the number when taken k at a time from a collection of n objects is denoted by Cnk as listed below. So you've got C62 is 15 and so on. Cnk is often written n over k in brackets, sometimes called n choose k. Later in the 6th century AD, the astronomer Varahamihira calculated the number of ways of selecting 4 perfume ingredients from a collection of 16. And he obtained the correct answer of 1820. He surely didn't list all these combinations. So how might he have found this number? I'll come back to that in a minute. But first, in how many ways can a given collection of objects be arranged? Consider this problem also from India. The Indian god Vishnu holds in his 4 hands a discus, a conch, a lotus, and a mace. How many arrangements are possible? And to answer this, we note that Vishnu's first hand can hold any of the 4 objects. His second hand can then hold any of the remaining 3 objects, and so on. And it follows that the total number of possible arrangements is 4 times 3 times 2 times 1, which is 24, which we call 4 factorial, written with an exclamation mark. And below we give the corresponding number, n factorial, of arrangements of n objects. A similar example from the 12th century concerned the god Sambhu and asked for the number of possible arrangements of 10 objects, ranging from a rope and an elephant's hook to, surprisingly, a bedstead and a dagger. With 10 choices for the first hand, 9 choices for the second, and so on, we reach the answer of 10 factorial, which is over 3 million. Also interested in arrangements, but in a musical context, was the French monk and mathematician Marin Mersenne, of Mersenne primes fame. These are prime numbers which are 1 less than the power of 2, like 7 or 31. In 1636, Mersenne published a book on universal harmony, which dealt with many theoretical aspects of music. And in particular, as you can see here, he displayed all the 4 factorial equals 24 songs formed by arranging 4 musical notes. And he then followed this with the 5 factorial equals 220 arrangements of 5 notes. And then he wrote out all the 6 factorial equals 720 arrangements of 6 notes, pages and pages of them, all written out in full. Now, earlier we met problems on combinations of objects. And to explore these further, we return to Varahamihira's problem. In how many ways can 4 perfume ingredients be selected from a collection of 16? If the order of selection mattered, there would be 16 ways of selecting the first ingredient, 15 ways for the second, 14 for the third, and 13 for the fourth, giving a total of 16 times 15 times 14 times 13 selections. And you notice that number is 16 factorial over 12 factorial. But here the order doesn't matter. The 4 ingredients can be chosen in any of the 4 factorials 24 ways, all giving rise to the same selection. So for the number of possible different selections, we divide by 4 factorial, giving 1820 as the answer. And in general, the number of order selections of k items from a set of n objects is this result. And as before, we denote it by Cnk. So let's look more at these numbers Cnk. Let's look at 2 important rules for combinations. Rule 1 is that for any numbers k and n, Cnk is Cn n minus k. For example, as we saw with Sussruta's medicines, C62 is the same as C64, with both being 15. And we can prove this algebraically using our formula for Cnk. But it's much more revealing to note that choosing 2 medicines is the same as ignoring 4 medicines. So C62, the number of ways of choosing 2 medicines, is equal to C64, the number of ways of choosing which 4 to ignore. And this argument works in general. Rule 2, our chosen equation, states that Cnk is Cn minus 1k plus Cn minus 1k minus 1. For example, if we wanted to know C73, number of ways of choosing 3 out of 7, it's C63 plus C62, which is 20 plus 15 by Sussruta's results, and that's 35. And again, we can prove this by algebra, but a combinatorial approach gives more insight. To do this, let's mark one of the n objects in some ways, for example, color it red. Then any choice of k of the n objects either excludes the red one, requiring us to choose k objects from remaining n minus 1, or includes it, requiring us to choose k minus 1 of the remaining n minus 1. So Cnk, the total number of choices, is equal to Cn minus 1k, that's the number of choices that exclude the red one, plus Cn minus 1k minus 1, the number of choices that include it. Well, this symmetrical pattern of numbers is known as the arithmetical triangle, or Pascal's triangle, after the French mathematician and philosopher Blaise Pascal. Here, the number that appears in row n and diagonal k is the combination number Cnk. So, for example, in the row labeled n equals 6, the entries 1, 6, 15, 20, 15, 6, 1 are the Sussruta numbers from C60 to C66. And there are several things to note here. By combination rule 1, each row can be read forwards or backwards. By combination rule 2, each internal number is the sum of the 2 numbers above it. For example, in row 7, each 35 is the sum of 15 and 20 in row 6. We can also look at the diagonals sloping downwards from the right. The diagonal k equals 0 is all 1s. Diagonal k equals 1 lists the natural numbers 1, 2, 3, 4, 5, 6, and so on. While the diagonal k equals 2 features the so-called triangular numbers 1, 3, 6, 10, 15, etc., shown on the right, making triangles. Further diagonals then contain higher dimensional analogues of the triangular numbers. Now, the combination numbers Cnk that appear here are often called binomial coefficients because they arise when we multiply out powers of a binomial or 2-term expression such as 1 plus x. For example, if we multiply 1 plus x to the 6th, we get the expression below where the coefficients 1, 6, 15, 20, and so on are again just the Sussruta numbers. Well, the arithmetical triangle has a long history predating Pascal by several centuries. For example, the top diagram, dating from around 1200, appears in a book on calculation from Marrakesh, while below it is a Chinese arithmetical triangle from 1303. Interestingly, it contains an error. One of the entries in row 7 is 34, when it should be 35. Many other versions appeared in Europe from the 16th century onwards, but it was Pascal who gave the first modern treatment of the numbers C and K, linking the different ways in which these numbers can arise. His version on the right appeared in his treatise on the arithmetical triangle, which was published posthumously in 1665. And whole books have been written on Pascal's triangle. To finish this equation, we can even obtain the Fibonacci numbers from it. Just add the numbers along the diagonal lines shown here. So these give 1, then 1 plus 1, which is 2, 2 plus 1 is 3, 1 plus 3 plus 1 is 5, and so on. Finally, our fifth equation. This arises from the geometry of fractals, which differs significantly from the traditional geometry we grew up with. We'll look at some fractal patterns before taking a different approach, where the central figure was Benoit Mandelbrot. But before I introduce fractals, here's a story about a young Swiss alpenhorn player. He was madly in love with a young lady in his alpine village and decided to serenade her with his finest and longest alpenhorn. In fact, it was infinitely long, being obtained by rotating the hyperbola y equals 1 over x, where x goes from 1 to infinity around the x-axis. But when he tried to play it, it wouldn't work. It had become rusty and its inside surface needed a fresh coat of paint. But on calculating how much paint to buy, he found this to be an infinite amount. In desperation, he sought help from the village mathematician, who calculated the volume inside the alpenhorn and found it to be finite. And the solution was now simple. Pour this finite amount of paint into the alpenhorn, then pour the remainder away, leaving a coating of paint on the inside. The young man did so. The alpenhorn worked perfectly. The young lady was delighted, and the young couple lived happily ever after. Well, what's the relevance of this story? To answer this, consider the question, how long is the coastline of Britain? Viewing the map from far away, we might try to estimate the coastline's length. But as we zoom in to become closer, we find hidden bays and inlets and more twists and turns in the jagged coastline. And the closer we get, the larger and more accurate our estimates become, eventually growing without limit. So the coastline of Britain has infinite length, even though it encloses only a finite area. This situation recalls that of the alpenhorn, whose inner surface had infinite area, while enclosing a finite volume. And the jagged coastline of Britain, with its infinitely many twists and turns, is an example of a natural fractal curve. We now consider two further examples, and we'll see how these strange objects share properties that challenge our traditional views of geometry. Now, many curves are smooth everywhere with no corners, like the curve at the top left. A simple example that fails this test is the V-shaped curve next to it, which is continuous, but it has a corner when x is 0. And it's not difficult to draw similar curves that are continuous everywhere, but have corners at a finite number of points, 2, 3, 5, 100. But in 1872, the German mathematician Carl Weierstrass shocked the mathematical world by describing a continuous curve with a corner at every point. In 1904, the Swedish mathematician Helge von Koch produced another continuous curve in which every point is a corner. This was his snowflake curve. And to construct it, take an equilateral triangle, divide each side into 3 equal parts, and then replace each middle third by the other 2 sides of a triangle to give a peak. And this produces a star shape with 12 sides. Next repeat the process on each side of the star and continue in this way forever. And this ultimately yields a snowflake, a continuous curve with corners everywhere. And it also has other interesting properties. Because each stage of the construction increases the curve's length by a factor of 4/3, the snowflake curve has infinite length, but it also encloses a finite area, which turns out to be 1.6 times the area of the original triangle. So like the coastline of Britain, it's of infinite length but encloses a finite area. And this curve also exhibits self-similarity. If you zoom into any part of it, this produces ever smaller appearances of the same pattern. And this property of self-similarity at all levels is a fundamental feature of fractal patterns. Another well-known fractal pattern was introduced in 1915 by the Polish mathematician Wacław Sierpiński. It also exhibits self-similarity, with many smaller versions appearing as we zoom in to examine it in greater detail. And to construct it, as shown above, we take a solid equilateral triangle, split it into 4 smaller triangles, and remove the interior of the inner inverted one, leaving 3 smaller equilateral triangles. We then repeat this process for these smaller triangles and continue in this way forever. An unexpected observation here is that we can also obtain the Sierpiński triangle from Pascal's triangle. To do so, we color every odd number gray and every even number white, and part of the result is shown here to give you the idea. Now, around 1975, a completely different approach to obtaining fractal images was being developed. Benoit Mandelbrot was born in Poland in 1924, lived for some time in France, and eventually settled in America. Here he introduced the term fractal, meaning broken, to describe the intricate nature and self-similarity of these objects as rough or fragmented geometric shapes that can be split into parts, each of which is at least approximately a reduced size copy of the whole. And his contributions to this area greatly influenced mathematics in the second half of the 20th century, as fractals influenced a wide range of topics, from chaos theory and the diagnosis of cancer, to the flow of air around an aeroplane wing, and the study of planetary motion. Fractals are everywhere. And to describe and to understand his approach, in the last few minutes, I'm going to consider first linear transformations of the plane of complex numbers, in which each point z is mapped to rz plus s, where r and s are constants. So examples of such transformations listed below send each point z to z over 2, half of z, and to z plus I, where I is the imaginary square root of minus 1. So what happens when we apply such a transformation repeatedly? Starting with a given point z0 to its successive iterations z1, z2, and so on, do they ultimately converge to a finite point, or diverge to infinity, or neither? And in each case, an associated recurrence relation takes us from each point zn of this iteration to its successor zn plus 1. So for z goes to z over 2, with initial point z0, the first iteration halves it to give z1 as z0 over 2, second gives it over 4, the third gives over 8, and so on. So here the successive points zn shrink to 0, whatever the initial point. Whereas for z is z plus I, with recurrence relation zn plus 1 is zn plus I, the first iteration sends it to z0 plus I, then to plus 2i, plus 3i, and so on. So here the resulting points diverge to infinity for all initial points z0. Now we come to the crux of things. If we move to quadratic transformations, here each point z is mapped, well, it looks like rz squared plus sz plus t, where rs and t are constants, but that's jolly complicated. But fortunately, a change of variable simplifies this to z goes to zn plus c, z squared plus c, where c is a fixed constant. So here the recurrence relation is zn plus 1 is zn squared plus c, our equation. Now the interesting thing is we can restrict our attention to these examples for different values of c, and amazingly, changing c has major consequences. For each value of c, we'll distinguish between the set of initial points that stay finite, ultimately, and those that go to infinity. And the boundary between them is called the Julia set, after the French mathematician Gaston Julia, who studied them in the early 20th century. And when C is 0, we have the transformation Z goes to Z squared, and this repeated squaring fixes the point 0, sends the point a half to a quarter, 16th, and so on, in other words, converging to 0, sends the point 2 to 4, 16, 256, going to infinity. And in fact, looking at the picture, all the shaded points within the circle on the left converge to 0, all the unshaded ones outside it diverge to infinity, and the Julia set is actually the circle celebrating these. Now, when C is minus 2, we have a very different situation. Look at this line. Here, every point on the line between minus 2 and 2 stays finite. Every point off the line diverges to infinity, and the Julia set is just the line segment itself. And the case C equals minus 1 is even more bizarre, as we see on the right. Here, every point within the shaded region stays finite. Every point outside it diverges to infinity. And the Julia set is the boundary of this region. So Julia sets vary widely for different values of C. Here are 3 more of them. Note that the first 2 are connected, that is in one piece, while the last one, sometimes called the seahorse, breaks into many pieces. And this difference turns out to be crucial. So we now arrive at last at the Mandelbrot set, which will be familiar to some of you. The celebrated fractal patterns arises in various ways. An early version had been presented in 1978, but it was Mandelbrot in 1979 to 80 who analyzed it extensively by computer, describing it as an astonishing combination of utter simplicity and mind-boggling complication. As you can see, it's symmetrical about the real axis and resembles the cardioid or heart-shaped curve with infinitely many circular disks and other bits emanating from it. And as with other fractal patterns, it exhibits self-similarity in abundance. So to end with, let me tell you how the set is defined. One way involves Julia sets. Most of our earlier Julia sets were connected in one piece, but the seahorse was not. And based on this idea, the Mandelbrot set consists of all those complex numbers C for which the Julia set is connected. So for our earlier examples, we see that the Mandelbrot set includes 0, minus 2, minus 1, I and a quarter, but it includes that seahorse minus 3/4 plus a quarter I. There's an alternative definition which involves the iterations of z squared plus c when the initial point is fixed at 0, and you get the Mandelbrot set for those points for where the iteration remains finite. So, as you can see, the Mandelbrot set is highly complex. Indeed, Guinness World Records has claimed it as the most complicated object in mathematics. As I mentioned earlier, self-similarity is everywhere, and the more closely you look at it, the more convoluted its structure seems to be. And here on the right, you can see the result of zooming into just one of its protuberances. Quite amazing. So to end with, this Mandelbrot set also exhibits great beauty and gives rise to a wide variety of intricate and attractive images. Described as fractal art, these date from the mid-1980s onwards and regularly feature on posters and T-shirts. And this unexpected connection between science and art was a great joy to Benoit Mandelbrot, who had done so much to develop it. So finally, if you want to explore these ideas further, there are a number of books on equations. There's one by Ian Stewart, which has equations from both mathematics and physics. And then there's one on the right, which was published just a few weeks ago. Thank you for listening.